Hello, everyone, and welcome to this webinar hosted at a slightly later time than our usual webinars. Our speaker is from California, so it's early in the morning for him, and it is a pleasure to announce that this speaker is Professor José Andrade from Caltech, who will be talking about what he calls the granular genome, an alternative to constitutive models, which should be really interesting. So just before we get started, a few announcements. First of all, just a list of the program for the rest of this year. Almost, we have another couple of talks in December that are falling into place at the moment, but it's a fortnightly event, and it'll definitely continue until the end of November. And also, as usual, you're very welcome to ask questions. You can either type those questions into the Q&A box if you press the button there in the Zoom panel. You're welcome to also type those questions while talk is ongoing, and then we'll take them afterwards. Or if you prefer, you can raise your hand, and then I'll unmute you and you can ask your question in person, and maybe we'll even have a bit of a debate, as you could say, a bit of a warm-up to the big one later tonight. But let's see about that to the talk first, and I'll hand over to you, Jose.
Thank you, Christian. So should I share my screen?
Yeah, you share your screen, yeah.
You cannot start screen share while the other participant is sharing.
Okay. I'll stop mine then.
Thank you. All right. Can you see my screen?
Yeah.
Okay. Well, thank you very much, Christian, for the invitation. It's a pleasure to be here. Welcome everybody to this webinar. It's a pleasure for me to be here today. As Christian said, I'm from Caltech, and it's a real pleasure to come to this webinar and show to you a little bit of the work that we do in my lab. Our lab is called the COSIMO lab, that stands for Complex Systems Modeling Lab. And of course, we have a great interest in granular materials and in geomechanics. That's the origins of our lab, but we are rotating or pivoting towards more general systems, like complex systems that include granular materials, of course, and granular systems. But today I thought I would show you the work we do with granular materials, and in particular talk about the granular genome, which we believe is or could be an alternative to constitutive modeling, and I'll show you our reasoning behind that. But before I do that, let me acknowledge my collaborators for this talk. So a lot of the work you're going to see is from my student Konstantinos Karapiteris. Kostas is doing a lot of work in trying to probe granular materials. John Harmon is another PhD student of mine. A lot of the breakage work you're going to see comes from John Harmon, how we split particles. Reid Kawamoto is the person that implemented the first generation of what we call level sets, discrete element methods. And our colleagues from Grenoble, Chino Vigiani and Eduardo, every single X-ray computed tomography image that you will see comes from their lab, and they provided us with inspiration over the years. So just a brief remark, if you've been to the Vargalakis lecture, maybe this is your time to ditch out. This is going to be pretty much a repeat of a Vargalakis lecture. I thought that since I have a captive audience today, I would repeat that lecture for the sake of our community and also in honor of Yanis. But with that said, and with that caveat, let me get started. So I want to start by, of course, quoting Terzaghi, who many years ago, and actually 100 years ago, already understood a lot of the concepts that we're going to be discussing here today. And so I'm going to read this with you just to make an important point. That Terzaghi thought that Coulomb purposely ignored the fact that sand consists of individual grains and dealt with this sand as if it were a homogeneous mass of certain mechanical properties. And as you know, this is the basis for continuum mechanics. And the idea proved very useful, but it developed into an obstacle as soon as this hypothetical character came to be forgotten. So we kind of forgot where we started and sort of took continuum for granted. That's what Terzaghi is saying, and I agree with that. The way out of the difficulty lies in dropping the old fundamental principles and starting again from the elementary fact that sand consists of individual grains. So this is precisely the philosophy that we want to embrace today. Yes,
Jose, are you still on the first slide? Because we can only see the first slide. I don't know if something has gone wrong, if it's frozen or something.
Oh, it might be frozen. You should be seeing a picture of Terzaghi.
No, yeah.
Okay, how about now?
That's it.
Okay, so I might have to stay here on this view because apparently when I go to the other view, now how about here?
Yeah, still Terzaghi.
You see Terzaghi?
Yeah, try to go one. Try to advance one.
Can you see the outline now?
No.
No. Okay, now you can see the outline.
Yes.
Okay, that's a problem. So, okay, let's try to go like this. Let's see how far we can go. I hope the videos will display in this view. Let's try it with this. Okay. So here's the outline for the talk. So we're going to embark in a little bit of philosophy, you know, the idea of abstraction, the idea of genome, and also constitutive modeling. Then I'll show you some physics-based models that are inspired by X-ray tomography and the LSDM modeling. And then I'll show you some current work that we're doing in our lab, in our Cosimo lab, and then I'll close. Let me start with a bit of philosophy. And so, you know, there's a slide showing what we really want to do in engineering. So if you see my cursor here, there's a bullseye that shows the target of what we're trying to do. We're typically trying to design things. So here, an example is the design of turbines, offshore turbines. You know, this could be in Norway or in California, and you're trying to design these beautiful structures that need to sustain millions of cycles of loading, maybe for very, very small strains, but millions of cycles, very low amplitude. And the way we do this as engineers is we start to construct abstractions that will represent or simulate or model these structures, right? So we may have a pile that has some springs attached to it that are there to simulate or model the interaction with the soil. And then here we put some of our loadings, you know, the moments and so on. So, you know, you can think of these PY models as the first representation of abstraction. And then if you keep going towards more physics-based, right? So here's what I would call the state of the art today, right? So here's continuum modeling with plasticity as the cornerstone of material behavior, right? You see your pile again, no longer springs and dashpots needed, right? You have all these finite elements surrounding the pile, and the interaction is very nicely captured. But the key is that you need a constitutive model, say like Sunny Sand or any other, that can really represent the behavior of the sand and the soil around. And then if you go one more level down, if you will, you can then look at the real granular physics, which is what Terzaghi was saying is really going on, which is the interaction of grains that are that are in contact with each other, that are rolling, maybe they're breaking apart. And from these, all the other abstractions emanate. But I want you to understand that we are increasing in abstraction as we go from left to right. And the most basic way of representing the physics that we have in our problem is the grain scale. Now, of course, we don't want to design offshore structures looking at the grain-to-grain interaction, and that's one of the points I want to make here, that we're not naive. It would be futile to design structures with grain-to-grain interaction models. What we do want to do is inspire models as we go up in the level of abstraction. And so the question becomes, how do we do that? And that's where the concept of a genome comes in. So a genome in a biological system is the entire set of hereditary instructions that tell your body, say if you're this beautiful frog, your genome will tell the frog how to build its body and its ingredients, how to run the biological system, and also how to maintain it. And every single living organism works with this structure. In the case of humans, we have 3 billion DNA base pairs that make up the human genome, and those are the set of instructions that tell your body and my body how to do everything. And we believe that we can borrow this concept and we can adapt it to geomaterials and to granular materials, as I will show you in a little later. We believe that there is such a thing as the granular genome. And the hint for this is this missing link that we all know that exists today in the way we model things. So when I was an undergrad, and all of you that have been undergraduates in civil engineering and you took soil mechanics, you're presented with this kind of charts that I'm showing here on the left, right? When you learn the soil classification system, for example, you learn to plot this grain size distributions for different soils, and based on grain size distribution, you can classify whether something is a sand or a silt and so on. And then if you get into the really fines, then you do plasticity limits and so on. But there are these ideas embedded in the way we classify materials, and also we know that that classification affects deeply the mechanical behavior of the material. So we know that from grain size distribution, from shape, and so on, properties come off and properties are determined. Yet, when we go to calibrating or tuning our constitutive models, all of these descriptors, these physical descriptors, go out the window, and we focus on trying to match stress-strain curves, like the ones that come from the triaxial cell, and the physical descriptors are completely lost. And so the continuum models do not explicitly account for grain scale descriptors today. And because of that, there is a lack of understanding, and we claim even poor predictive capabilities. So in order to remedy this, the idea is to come up with a hypothesis that says that there is something called the granular genome, or the DNA, where the DNA can be defined as the grain scale information that encodes everything that is needed to define the granular material and its behavior. So examples of DNA could be grain size distribution, the shape, the mineralogy, okay? And so here's the DNA of the material, and then when you combine the DNA with something we call the state, that we've known for a long, long time matters a lot in these materials, then you are at a point here at the intersection between your DNA, which is ingrained, or if you will, and implicit in the material, and the current state. And then what you want is depart from that intersection via some boundary conditions. Maybe you're perturbing the material in a certain way, and out will come behavior. This is not new in the sense that models operate more or less on this paradigm already. The only innovation here is this explicit accounting for the existence of the DNA. Current models have proxies, if you will, plasticity parameters and so on, that will try to represent this DNA. Here, the idea would be to explicitly have the DNA be part of a modeling paradigm. And by behavior, here will mean kinematics, kinetics, and also stress and strain. So we're taking a deeper definition of behavior. So the Moore Coulomb paradigm, which is the sort of cornerstone of our constitutive modeling, introduced this beautiful notion that the shear strength in the material was directly proportional to the compressive or the isotropic stress sigma via some mobilized friction coefficient or mobilized friction mu. And we've sort of embarked on that idea, and we've developed constitutive models that more or less expand on this idea. Mu here is this implicit descriptor of DNA, if you will, but it's really not DNA, right? There's nothing in here, there's nothing in mu that says anything about the grain size distribution or the shape of the particles or anything like that. So this is a modern example of a constitutive model. This is the Norsand model that I worked on during my PhD. And so a successful constitutive model would have a series of parameters. In this case, we have about a dozen parameters. Many of them, we have no idea what their significance or what their physical meaning is. For example, there's this parameter in this model called the hardening constant, which is essentially a knob. And many of the others are really just geometrical knobs, if anything. And so what you would do as a constitutive modeler, this is what I did for my PhD, you would have a series of experiments, say under triaxial compression, loose and dense sand, and you will calibrate this dozen of parameters to match those curves, both the stress and strain and also the volumetric deformation. Right, and then you would declare victory if you went to another set of experiments with the same sand, say under plane strain compression, and you were able to predict, right, the stress strain curves and also the volumetric deformation. And so I declared victory back in my thesis by saying, look, I can calibrate the model with some rational set of dozen parameters, and then I can go and predict at the stress strain level. Now, there are two shortcomings with this. First is that you're blind, more or less, in your choice of parameters, and it's a non-unique set. And two, your predictions are confined to the macro, right? You can only match stress strain curves. You're essentially curve fitting when you're doing that. So there's got to be a better way. So the idea here is that there are these physics-based models that can do better in many ways. And let me define what I mean by better. So let me first expand the definition of prediction. So let's go beyond the stress strain curve, the macro, and embrace the fact that you have a mesoscale, say the one at the scale of shear bands. And then you can even get more greedy and define a scale at the grain scale where you have information now, like forces and definitely kinematics. So let's redefine a predictive model as one that actually compares well with experiments across these different scales. So I want you to know that that's a radically different definition of prediction. It doesn't only live at the macro scale anymore. It lives at a set of different scales. And the data will come from X-ray computed tomography, mostly, at least in this talk. So where you have these experiments, you see here the cell, right? You're doing triaxial compression as you were doing before, as you typically do in any modeling exercise. But the additional information here comes from this X-ray transmitter that goes through the sample, and then the information gets picked up by the receiver, and you see things like you see on the right-hand side of the slide, where you see a computed tomography image of the sand. And when you stitch that all together in 3D, you get your typical stress strain curves, as you do in any triaxial cell apparatus. But on top of that, you get this series of snapshots in 3D that tell you where your particles are at any instant in time. So the point is that you have information that allows you to know what's going on at these three different scales, right? You have the macro, you have the meso, and you have the micro. In computed tomography, you only get kinematics. You don't have information of forces. But okay, we're going to take that data, and we are going to use that data to capture the morphology, and like I said, try to also capture the kinematics of particles. So we can go from these images of particles and convert them into models. So here, for instance, I'm showing a three-dimensional picture or rendering of a sand grain on the upper right corner that emanates from X-ray computed tomography. And so these grains are no longer pictures, they're mathematical representations of grains. And so the challenge for DEM becomes how to absorb all of that information. So these are current particles being used in the state of the art, right, that go from clustering particles all the way to potential particles and polyhedra. Here, I'm going to offer you an alternative called level set discrete element method that goes from an image, or it can go from an image, like you saw in the computed tomography, all the way to a level set representation, or what we call an avatar of that particle. So every time you see a picture of a particle, I want you to think that that picture can become an avatar. And what that means is that there is a mathematical rendering of that surface of that particle, and therefore you can use that rendering to do computations, to do calculations. So these are just examples of different particles, all the way from Houston sand to quickcrete, that you can go from the image, the picture in the X-ray CT, to a mathematical representation of that particle, regardless of the complexity in the shape. There's really no boundaries here. You can do convex, concave, sharp, rounded, it doesn't matter. The level set can capture every single shape that you feed it. We can make you a particle, and that would be fine. The level set could represent the shape of your body. And so, in brief, just to summarize what the model is that the innovation here is that it's your good old discrete element model, but with the ability to capture particles, any particles, and their shape with these level sets. And so those are your geometric bases. You can do arbitrary shapes, and you can do this in a pretty inexpensive way. You can do, at this point, we're doing hundreds of thousands of particles. We're getting very close to millions, thanks to parallelization and a little bit of smart code. But we haven't really pushed the envelope in level of sophistication. So here's just a summary of how the model works. So you have a level set that represents the boundary of the particle. The contours tell you the distance to that boundary, and then you can use that distance function to do contact mechanics, okay? And all of that is defined in our papers. And then you feed that into your usual Newtonian equations to solve for forces and moments and update the kinematics. Okay, so, and you can use explicit DM, you can use implicit DM, what people call contact dynamics. Really, you can implement the favorite flavor of discrete modeling that you like. But the point is that you can now represent these shapes arbitrarily. So we're going to test this hypothesis that there exists such a thing as DNA. So the idea is to extract the granular genome from an X-ray sample. So from an X-ray sample, we have everything that we can define as a genome, right? We have the shapes, we have the grain size distribution, we have even the location of the particles. And then, so the question is here, can we impose the state, you know, the same pressure, for instance, the same confining pressure as in the experiment and the same density as in the experiment, and then probe with the same boundary conditions and obtain the behavior that we see in the experiments. And by behavior, again, I want you to think in an expansive way now, not only macro stress strain, I'm talking meso and even micro, right, granular scale with the kinematics. And so we go from an X-ray computed tomography of about 60,000 grains, 54,000 grains, and we do a grain-to-grain model of that initial DNA. And so every grain has its avatar in the same shape and location as in the original sample. And then we introduce the same boundary conditions, the same confining pressure, and the same vertical deformation, excuse me, that is imposed in the experiment. So let's see if this shows. There are a couple of movies here. Can you see the movies, Christian? Do you see this movie?
Yeah, they're running, sort of. Yeah.
All right. So here on the right, you can see the ultimate deformation of the sample, right? How from the vertical deformation of the platen, notice that the platen is allowed to tilt. You get this beautiful deformation pattern. You see a shear band actually that forms and so on. So you're starting to get very realistic deformation patterns that seem to match what you expect in reality. Here is starting to get more quantitative. This is a slice of that same experiment showing the vertical displacements. And here it's just a rotated image of the deformed sample. Okay, but now let's start to make some comparisons with the data. So here is how the model compares with the macroscopic response of experiments. So this is what your good old constitutive model would attempt to do, right? You would try to match the stress strain curves and these dilatancy curves. And if you could do it with a suitable set of parameters, right, like the ones I showed you over here, in my constitutive model of north-cent, you would declare victory. And so you can see that the discrete element model, the level set, does exactly the same thing that a continuum model would do. So at this point, we are tied with the continuum model. With one caveat, we haven't calibrated a dozen parameters. All of our parameters are coming from the properties of the grains. We're not tuning anything. But we can push the boundary of the model even further and ask it to make predictions about physics that are happening at lower scales. So here is the mesoscale. So on the top, you see the experiment. On the bottom, you see the computation, and you're hard pressed to tell the difference. The location of the shear band, the thickness of the shear band, the timing of the shear band, it's all predicted by the model. And notice that even the amount of strain inside of a shear band is matched by the model. And again, this is something that a continuum model would really struggle representing. Maybe it would get the direction of a shear band, the angle, but it would be almost impossible for a continuum model to detect the exact location of a shear band and definitely the strains inside of a band. And then if you get even more ambitious and you ask the model to predict at the next level, which is the grain scale, these are the particle rotations, the experiment in the top, the model at the bottom, you see again that the model is really able to replicate the grain scale kinematics, something that now, you know, continuum is hopeless by definition, right? Because it's not designed to do that. And then you can use this model to tell things like also the evolution of the force chains. So this is the same numerical experiment where you see those beautiful force chains collapsing and buckling. This is actually a better rendering. I hope this plays. But here you see on the left, you see the kinematics. So on the left, we're plotting the displacement and rotations. The rotations are in white and the displacements are in purple. And on the right, you're seeing the corresponding kinetics, the forces that are happening at the same time in the sample. You can see the shear band. You can see all of those force chains. In fact, you know, we're displaying these 3 columns of grains that are initially vertical in the experiment, and you can see how they collapse and how that is entangled with a whole complex entanglement of force chains that are collapsing as your shear band evolves. So this is a beautiful rendering that shows you how kinetics and kinematics are linked, intertwined in this samples, and how we can use this data for the future of constitutive modeling. But you don't have to live your life just quasi-statically. You could do things dynamically. So here are some cyclic experiments of triaxial compression and extension in sands again. And here you see 3 load, unload loops that, again, a constitutive model would be required to literally go through those loops, right, and try to match that stress strain curve. And you know, you would declare victory if you can match that again after some tuning. Here we don't have to tune anything. We use the same parameters we had before, and we just go through these 3 different load unload loops in stress strain curve, and we match the behavior, you know, really in a remarkable way at the continuum level, at the macro level. But we can go further. We can look at the mesoscale information. So this is coming from the experiments from Edward Ando and Chino Vigiani. So you see this necking when they do extension of their sample in the lab. So this it's reminiscent of a metal. So this is 15% extension, for instance. And then you require your model to try and tell you what happens at 15% extension, and the similarity and the level of match is just remarkable. So I think it is clear that the DNA hypothesis is real, and it's been confirmed under a number of experiments. You can start with something that tells you what the DNA of the material is. You put that together with the state, and that should be your initial starting point, your initial conditions, if you will. And then you can perturb that initial point in your DNA state space, and out comes the behavior of the material. And now we've redefined behavior as something that exists in the macro, the meso, and the grain scale level. And so it's really remarkable and powerful to embrace this DNA hypothesis, this granular genome, and use it for modeling granular materials. So let me show you, in the time we have left, some of the things that we're currently working on, and then leave plenty of time for Q&A. So I told you earlier when I was starting this talk that our goal was not to replace continuum mechanics or constitutive modeling. Our goal is to further inform it, to inject the information that we know about these materials at the grain scale and the mesoscale and help develop the next generation of physics-based models. And so one of the things that we're interested in, and Konstantinos Karapiperis in our group has been pushing this idea, is of virtual experiments. So this is something that this framework can be very useful for, because when you do experiments, you spend a day, for example, getting some of those triaxial compression tests that I showed you earlier with the X-ray tomography images. You can only do a handful of those, right? Because you need a person in the lab, you spend a day, it's very expensive to do a test. And not only that, but to replicate the same initial conditions is very difficult, if not impossible. But if you think about it, with virtual experiments, you don't need a person in the lab, and you can replicate the initial conditions and the boundary conditions of your experiments with a level of fidelity that you just don't have in the physical experiments. And then you don't need a person anymore. You can have this running in hundreds of computers at the same time. So you can run literally thousands of virtual experiments at a time in a fraction of the time that you would do it, infinitely lower time than you would do in physical experiments. But of course, you would have to be certain and sure that those experiments are reproducing reality. But I think that by now we have established that they are. So you start by, of course, doing some characterization of your DNA. Oops, sorry. And then, let's see, this one has an animation. Let's see if you can see it. And then you go to the material characterization, where you would get your parameters from the physics. So these are some beautiful experiments that show the contact properties of grains, so that you can feed into your model, not calibrate, not tune, but feed the exact measured, say, coefficient of friction. And then you would have an avatar or a computational model now, or a virtual sample that you are ready to test. So those are the ingredients, okay? And so here is an example of a series of tests that you could do. So here's your virtual sample now. This is true triaxial. And you can control the boundaries and the level of, for instance, the level of isotropic preloading or anisotropic preloading, whether you're at point A or point B. And you can do this Rendulic plane probing as you do in any good old constitutive model, right? So you would go around the Rendulic plane with a given delta sigma, and then the outcome is a resulting delta epsilon, right? And so you get this response. So this is your input and this is your response. And you can do that at any level in the pre-compression space as you like, and then make comparisons to understand, for instance, the effect of anisotropic compression. You can also test the effect of loading and unloading. So for instance, with causes, we did probing at point B, but we also did probing at something we call B prime, which is we went out to a certain point C, right, in the stress space, and then we unloaded back to B prime, just to be able to understand the effect of loading and unloading and the changes in fabric. And sure enough, there is a significant difference between the response we get in B and the response we get in B prime. And so here is just a summary of what those probes look like. So here is the the response you get at A, the purely isotropic state. This is the response you get at B. This is your anisotropic state that was not over consolidated. And this one was the one that was overstressed all the way to point C and then back to B. So this is what we call B prime. The first thing I want you to notice is how remarkably different B and B prime are. And the other thing I want you to notice is how you can readily read off the total strain deformation that you get in these samples, the elastic response, and the plastic response. And again, this is for the constitutive modelers in the audience. This is the kind of information that every model needs. And now you have a machinery that is able to give you all the data you want in order to come up and fine tune your next constitutive model. So no more excuses that we don't have enough information. All the information is here. It's a question of mining it. In fact, again, you can even go further and ask for micromechanical information that you just don't have access to experimentally. So you have here, for instance, the amount of plastic dissipation, and this is a remarkable result. We see that the weak network, so the network of forces that are below the mean in the sample, are the ones that do the most plastic dissipation. Makes sense. They're the less confined, right, kinetically, so they're more able to accommodate, and therefore they dissipate most of the energy, whereas the strong network does very little of that dissipation. And so you can now dissect your sample everywhere and see where things are happening. You see a bit of a shear bend here and the amount of dissipation that's going on. Here is the fluctuations in the contacts, etc. You name what kind of variable you like to look at, and these models, these virtual experiments can give that to you. Here is now an image showing the rearrangement in contacts as you go from one point in the probe to another point and then to another point. So here you see how your contact forces are evolving as a function of the deformation in the probe, and how a point on the one side of the ellipse is completely different from a point on the other side of the ellipse, even though, macroscopically those loadings seem to look very, very similar. Okay, so let's now approach the end of the talk. Just before we do that, you can then get your good old yield surfaces that you like to have in your plasticity models, right? So again, you see that from all of this, you get the beautiful shape that you would expect, right? That sort of triangular shape in the deviatoric plane. We also discovered that as plasticity evolves, that shape goes from something that looks more circular to something that looks more triangular. There is definitely non-coaxiality, so we can test things like associativity rules for plastic flow. We can start to construct plastic potentials. We can really build models from the grain up and see how they compare with our good old constitutive models that emanate from continuum mechanics. But let me just finish by showing you other things beyond just good old constitutive modeling. This is an area that we are very much in love with, which is grain fracturing. Again, these are beautiful images coming from the lab, where you see a particle that is loaded vertically, and then as a result of that loading, you see how this particle fragments. And as modelers, we would like to match this kind of behavior with a model. And so lots of work happening in this field in particle breakage science, experimental work coming from the Harley lab, This is a recent paper. Of course, Itai and Nav from Sydney doing continuum modeling with this breakage parameter B, right, that goes from 0 to 1 as your breakage evolves. Al-Shibli doing finite elements to break these particles using fracture mechanics, you know, sort of a continuum approach at the particle level. And then our recipe for this problem is to do our level set DEM, but enable it with the ability of splitting these particles. And here's just some eye candy of the kind of things that the model can do. So here you see a tube with some two-dimensional particles and how they're breaking as we come down. Here's the 3D version of that. You see how the particles are splitting and breaking apart. And here is something extreme. So here's a wall that is initially a continuum wall, a pristine wall, and then we break it with a mechanical device. So
José, that video didn't play. Maybe you can. Is there another way?
Here
Yeah, we go.
the videos. So this is a three-dimensional version of the 2D video. So you see all those particles breaking, and this is a wall that it's initially pristine, and then we come in with a mechanical device and completely tear it apart. So we can go from something pristine and continuum to fragments by allowing these level sets to split. So we have a paper that just came out with Harmon, John Harmon's work that explains exactly how to do that. And he shows some examples. So I won't get into the details, but essentially you use the external loading, the forces to compute the average stress in the particle. You don't have to do that. That's how we choose to do it to make it faster. And then using that average stress in the particle, we're able to split our particles. And we get remarkable similarities with experiments. So here's a jaw crusher experiment. Let me see if this plays. Maybe it won't play. So do you see this video?
Yeah, no, it's not playing. What you did before somehow.
Yeah, every time I can, yeah.
Okay.
But it's under it's behind the image.
Okay.
Yeah, I'm sorry. So imagine, let me see if I can move this. Here we go. So this is the crusher. Here's the mechanical device, the actual apparatus. Here's a schematic of that crusher and the numerical simulation of that Harmon is doing. So your grains are going in, and the crusher is breaking those grains by essentially closing the mouth, the gap down here. And so people collect data from this experiment. So here's data from Johansson. So that's in the points here. So you start with some, again, with some DNA, some grain size distribution. So that's a black curve here. And you can plot things as your final grain size distribution as a function of that mouth. And you see remarkable agreement with the experiments and the simulations. And again, no tuning here. It's just coming out from the model. You can do the same thing with the odometer test. So this is the 2D version of that. People get things like strain stress curves, like this one here on the lower right. Again, you see that the matching of the stress strain curve is very good. Initial grain size distribution in blue, final grain size distribution in red. You can see that the model and the data agree really well. We're doing this with Northwestern now with the group of Giuseppe Buscanera with X-ray tomography, and the results are just remarkable in 3D. But you don't need to do just dry things. Now we have models that we're developing for sea ice, or you can. So those are these models here at the bottom. So the particles here that you see are satellite images of ice flows that are floating in the ocean. So we have a model that we're developing to simulate the migration of these particles. They break apart, they melt. The physics here are extremely rich. And now we have satellite images that can serve as analogs as those X-ray tomography images that I've shown you. So we're building those models as we speak. You can also look at water bridging, ice lenses and bridges that are acting in between particles. So this is a frozen sand, if you will, with some ice bridges in between the grains. We are building models that can represent this kind of DNA and also match the breakage of those ice bridges. And of course, we can go beyond grains and sands to particles that are fabricated and that are then embedded in some polymer. And let's see if this plays. So here you see a mechanical experiment of a material that is a composite material of these spherical grains that are that have this cohesive element in between them that is a polymer. And on the right, you see the macroscopic stress strain curve. And on the upper right corner, you see the deformed configuration of that material. And again, we have now models that can reproduce this with an amazing level of fidelity. And we're collaborating with material scientists to develop these metamaterials that can absorb energy in a way that just regular materials can't. And the basis here is this level set model that you can use to simulate. So let me just close by repeating what I've said, which is I think that curve fitting constitutive modeling is over. So if you're planning to devote the rest of your career to that business, I advise you to pivot. I think that the future is in physics-based models that can mine and take into account directly the very rich physics now that we are able to access through experiments or through virtual experiments, as I showed you. And you can go way beyond just dry, rigid grains. You can do fracture, you can do cohesion, and you can definitely incorporate the presence of fluids. With that, thank you so much for your attention. And if you're interested in our work, please visit our website at cosimo.contact.edu. Thank you so much. Great to be here with you.
Great. Thank you very much, José. That was a really, really interesting lecture. I think there should be quite a few questions that we can then go through. Before I'll just give a few minutes for those to come in and then ask a question myself, because when you started off, and also actually that's kind of the note you ended off, you finished off on, with the message basically that traditional constitutive modeling is over. Maybe that's taking it a bit too far. But I think you're right in principle, but there's still some pretty significant, obviously, let's say, technological, computational challenges to be overcome before we replace our constitutive models with, that would be some sort of multi-scale approach, right? Where you would somehow couple the grain scale and the macro scale, the boundary value problem scale in a kind of an automatic way. But what I found really interesting was what was your comments there on virtual experiments, which in a way sort of maybe ironically kind of breathe some new life into traditional constitutive models, right? Because you will definitely be able to calibrate them to a much greater extent in principle again than you are today, with the availability of a tool like this that well, it takes time and takes a bit of computational resources to run them, but that's nothing compared to what it takes to run actual physical experiments, especially when it comes to things like cyclic loading and sort of time-consuming experiments that need to be controlled quite carefully as well. So I thought that was really quite interesting, and I hope.
Yeah. So let me start by saying that, you know, I believe in freedom of thought, and I think that a person is free to pursue science, right, in the way that they choose to, right. So if someone wants to, spend some years in the lab calibrating current constitutive models, you know, more power to them. But I think what I said is that the future, where the real prize is, I think, is in developing a new generation of constitutive models that can really not just tune their properties better by the wealth of data that will come from, say, virtual experiments, but really to take it one step further and acknowledge the fact that there is data there that needs to be incorporated in the models directly. Think of fabric, think of grain size distribution, think of shape. These are things that models don't explicitly account for in general. And so what I said was this, this sort of old traditional modeling style. I have a bunch of, you know, properties, and I'm just going to tune them because now I have more and more experiments. I am saying that I believe that that is dead, in the sense that it's a business of diminishing rewards. But you know, but people are free to choose what they want to do. I think that there's going to be a generation of new models that will just abandon that uh, philosophy for a philosophy that explicitly accounts for micromechanical features, and that's what I meant by the end of you know, traditional constitutive models.
And what will those models look like? Are we seeing the beginning of that? Because I mean, as you mentioned as well, elastoplasticity has been a pretty powerful framework so far, right? I mean, it has its clear limitations, but is where do you where would you?
So that's a great question. So for example, I think that elastoplasticity or hypoplasticity, or you know, these frameworks will continue to be there, right? Because they give you a nice framework, right? Like a plastic flow rule, the concept of the beginning or the onset of plasticity. What I envision them having now is plastic internal variables, right, that are more physically representative, right? So instead of having PIVs that were completely obscure in the past, right, some tensor evolving as a function of lambda dot, you know, I teach this stuff and I love it, but I would like to have a tensor that has a physical name, that has, you know, some physical connection to maybe the DNA and how it evolves, and maybe make it evolve as a function of plasticity. Nothing wrong with that. All I'm saying is that, you know, we should make an effort to make those PIVs something that we can actually see in the lab and maybe measure more directly. But I think the framework will continue to be there for the years to come, unless someone comes up with a completely new framework, which is also possible.
Sure. Okay, let's take a few questions from the Q&A box. So there's a couple of questions revolving around clays, which is something that maybe you could just make a few comments on that. So this work here is mostly concerned with what we would usually call sands, right? Where we have grains of some reasonable dimensions, and but there are also clays.
Right.
Any comments to how to handle those materials in this type of framework, or does it require something very different?
Yeah, that's a great question. So as you said, this model right now is geared towards granular soils, sands. We haven't done work on clays. there are models being developed. Many of them are based on molecular dynamics to try to borrow similar ideas from this. We have thought of models that maybe define a sort of basic unit in place, like a globular unit, and then use that globular unit to construct a mechanical model that is somewhat representative of the microstructure of clays. The reality, though, is that clays are a completely different beast, and so we've sort of stayed away from it and focused on the contact-dominated type material, right, where breakage, where contact, friction are the main mechanisms. For clays, you would have to think of other features like chemistry and potentials in the presence of fluids that just it's just a completely different animal. So, but I do think that that's the next frontier, and I've seen some models that are coming out of MIT that look at molecular dynamics as a way of sort of building clay models from the particle up.
Okay.
So there is work in that area. It's just very much at its infancy at this stage.
Yeah. Back to the sands, and what I think is an interesting question. It goes as follows: undisturbed sandy soil samples for liquefaction modeling are very difficult and expensive to obtain, yet they're necessary to assess liquefaction susceptibility in some cases where empirical correlations fail. Could the level set DEN be used for that purpose? So basically cyclic undrained loading of samples that well, I mean, undisturbed, the question is what exactly that means, but you definitely in principle at least be able to assess the sensitivity to the grain size distribution, the void ratio, and these kinds of things.
Yeah, that's a great question. So with NGI, we have a project that we've been working on for a year or so now, where you could take a sample, maybe freeze it, so that you capture the in situ characteristics like the fabric of the deposit, and then you freeze that sample, you bring it to the lab, and then you do X-ray tomography of that sample to get its initial configuration and initial what we would call the DNA. And then you feed that to a level set DNA model, a level set DEM model, and you perform virtual experiments on the virtual sample now that is faithful and representative of the frozen ground sample that you took. And so we're playing with that idea. We've made some nice progress. We think it can be very useful, but that would be the way to do it. That way, we start with the real fabric as we captured it in the sample from in situ conditions, and we use the LSDM virtual machine to really probe things, drained, undrained, you name it. You know, that's the beauty of the framework, that you can then impose whatever boundary conditions you want, but at the same time have that representative initial fabric that we know is so important.
Yeah. A few technical questions, José, I was actually wondering about myself. The boundary conditions in the, or how you actually carry out those triaxial tests where you have really quite extreme deformations. Do you model the membrane as a shell type finite element maybe, or even with particles as well?
Yeah, so that's a great question. So here you see that extreme deformation. I didn't have a chance to say anything about the boundary conditions, but yeah, there is a membrane around the sample. The membrane is constructed by particles that are connected to each other. These are spherical particles, very small particles that are connected with each other by springs. So we model the ability of the membrane to stretch. So we are able to get the stretchability of the membrane, just like in your physical membrane, and also allow the sample to deform. As you can see, the sample has bulged. It feels that there is something constraining it, but it is also free to deform, just like in the physical sample. And then we impose a normal pressure, like we just do in the physical experiment, that is exactly the same amount of pressure that we impose in the physical experiment. So you could do this with finite elements as well. You could have a membrane that is finite element based and have it around the sample. Here we did it with DEM as well, because we felt it was a little more natural to do it in the framework of DEM. And the platen, as I said, all we're doing there is prescribing exactly the same thing as we prescribe in the experiment, which is the vertical direction of displacement. The platen is allowed to tilt, and actually we get exactly the same amount of tilting as in the experiment as a byproduct of this. So to recap, the boundary conditions are exactly the same boundary conditions as in the physical experiment, modeling a membrane as a membrane made out of spheres that are connected with a spring to give it that elasticity and deformability.
Yeah, yeah, interesting. Very, very nice. Water. There's a question that all these simulations here were done, at least the ones you're showing here, José, for dry conditions.
Yes.
Water can be incorporated, I guess, in one way or another. And we already talked about undrained conditions that doesn't need the incorporation of water, at least to do that at the sort of the sample level. But I'm assuming by water is meant the effects of capillarity and partially saturated conditions. Any thoughts on that?
Yeah, absolutely. And that's a realm, that's a space where very rich problems live, not only for liquefaction, but also for frozen grounds. But like I said, even beyond geomechanics, when you see sea ice mechanics, when you see cells also moving in fluids, even viruses like the coronavirus moving in fluids. All of those are particles essentially immersed in fluids. So we are very interested in going into that direction, and we are going into that direction. The question becomes, what do you want to model? So to model particles immersed in fluids, you have several options. You can integrate Navier-Stokes equation for the fluids and have a coupling term between the particles and the Navier-Stokes. You can do Lattice-Boltzmann for the fluids and couple the Lattice-Boltzmann with the DEM. There's a lot you can do in doing that coupling, so it becomes an act of modeling to decide how you want to manage that coupling. But yeah, that's an area of much interest. Right now, the main thing we're working on is sea ice mechanics, where we have these particles floating in the ocean. So there's a current underneath. So we solve the Navier-Stokes equation for the fluid underneath the particle. And then there's also the effect of wind at the top of a particle that also introduces some drag forces. So you can more or less explicitly introduce the effect of the fluids as they are more or less important in the problem that you're trying to couple. Of course, there's no free lunch, and the more physics you pile on, the more expensive these models become. And so you lose the ability to do millions of particles, you're down to thousands of particles.
Yeah, yeah. And one more question, I think this will be the last one, José, because we have to make sure also the video doesn't explode inside the recording, which will be online. You'll get a message on that once it's up. But something you haven't really talked much about, and that is the limitations with respect to the micro CT scans. What kind of grain sizes are you able to capture? This is a technology that evolves all the time. Where is that at the moment in terms of resolution?
Well, I think that would be a great question for my friend Chino Viviani. What I have seen are resolutions at the micron scale. So I've seen X-ray CTs down to 1 voxel length equal to 1 micron. And I'm sure that, this was already about a year ago. I'm sure that that boundary has been surpassed. So I wouldn't be surprised to see X-ray CTs that are sub-micron. What I understand is that you can go as small as you want, as long as you shrink your window. So if you really want really high fidelity, you just shrink your window so you see less of the forest and you focus more on the tree. The level of resolution that we have right now is sufficiently high to represent all the features that we need to represent in a computational model. So I don't think that the level of resolution from X-ray CT for granular mechanics it's a boundary. Maybe if you're trying to do the kind of problems that I'm showing in the screen here, if you're trying to look at the ice bridges or ice lenses in between particles, and you have very sorted sands with large grain size distributions, maybe you start running into issues of resolution. And like I said, what you would have to do is shrink your domain. But that would be a question more for the X-ray CT people. From a user of X-ray CT, I haven't discovered a boundary where I cannot access information I need as a modeler.
Okay. Well, that's great. I mean, that's, I guess, is what we need to know for the mechanical.
Now there is one boundary of X-ray CT, which is, as I've said several times during the talk, it doesn't give you forces. So if you want kinetics, if you want forces at the particle level, then you need to look at other methods. All that X-ray CT gives you is kinematics.
Sure.
Which is part of a story, but it's not the full story.
Yeah. You sound as if there could be a way of assessing forces as well.
Yeah, there are. I mean, people have worked on X-ray diffraction, also with optical methods. Photoelasticity, of course, was the first sort of progress we made in that area. But yeah, there are methods right now that give you access to forces, and so it's a really exciting time in our field where all the data we want is there. And that was my message. And I put in a provocative term, saying, constitutive modeling is dead, to hint and to provoke our colleagues to believe and understand that there is data at a level of resolution that just was not available 10 years ago. And as a field, I believe that we have to embrace that and think of ways in which we can revolutionize the field. And that's the message.
Yeah. Great. I think we'll end on that note, Jose. Thank you very much again for this really, really interesting presentation. And apologies to the attendees who questions I didn't get. I'll encourage you to get in touch with Jose directly after the talk. And just very finally, just a reminder that we'll be back in 2 weeks with another webinar, which I know will be very interesting as well. So thank you again, Jose. Thanks for attending, and thanks for your questions, and see you next time.
Thank you all. Have a great day. Bye.